Welcome to the seventh part of the series of lectures devoted to the RN software for filter design. In this part, we will talk about selective low-pass and band-pass filters with corrected group delay characteristic. The content of this lecture contains the following: correction of group delay for selective polynomial filters, then some comparisons will be given, then correction of group delay for selective low-pass rational filters with rational transfer functions, and finally correction of group delay for selective bandpass filters. The subject of correcting a group delay characteristic of a selective filter is one of the most intriguing among the transfer function approximation tasks. Here, one is to compensate the passband variations of the group delay to the maximal extent for a given approximation freedom, which is expressed by the order of the corrector. Usually, one is after equi-ripple approximation of the overall group delay, which is obtained as a sum of group delay of the selective filter and the one of the corrector. The area under the group delay curve is defined as twice k plus n altogether multiplied by pi half, where n is the order of the filter, having no transmission zeros outside of the omega axis, to be corrected, and k is the order of the corrector. For low orders of the corrector, one faces conflict between the equi-ripple approximation requirement and the large variations of the filter's group delay. That sometimes makes the equi-ripple approximation impossible. In general, the order of the corrector should be large enough to allow for enough flexible area to fill in the valleys between the passband maxima of the original group delay. A corrector cell in many technologies is more complex as compared to the cells realizing zeros at the omega axis. That means that one may search for optimum from the overall complexity point of view by using better approximants for amplitude approximation exhibiting lower group delay distortions. Here is the first example of correction of the group delay of selective polynomial filters. In this example, the ninth order LSM filter is taken and a corrector is synthesized of the sixth order, while the imposed requirement about the group delay error was 10%. As can be seen, the whole bandwidth, passband, is covered. Here is the same case, the same complexity, ninth order LSM with sixth order corrector, but the approximation error of the constant group delay is only 1%, which reduces the interval of correction to about 0.9. The counterpart of the LSM is the Chebyshev filter, and here seventh order Chebyshev filter is considered, which approximately has the same selectivity as the LSM of ninth order LSM. Here the order of the corrector, however, is 10, so that the overall complexity, so the overall filter order is 17, which is by 2 larger than the case of LSM filter. Of course, the same approximation error was used. Here again, 1% approximation is imposed. We are getting the same approximately interval of approximation of constant group delay with the 7th order Chebyshev, but 8th order corrector, lower order corrector, so that the LSM and the Chebyshev filter altogether are of 15th order, both. The main difference is here in the value of the delay and in the peak at the end of the passband. Here are these compared. So both filters are of 15th order, both have 1% error, and as we can see, the Chebyshev has larger delay in the passband and stronger peak. Here an example is given for correction of group delay for selective filters with rational transfer functions, selective low-pass filter with rational transfer function. As Zolotarev equiripple passband, equiripple stopband is used with the maximum passband attenuation of 0.2 decibels, minimum stopband attenuation of 50 decibels. The amplitude characteristic are renormalized so that at the band edge the filter to have 3 dB. It is a 5th order filter with 2 zeros at the omega axis. The corrector is the 4th order and the group delay error is 5%. Here is the group delay error exposed in order to see that due to the nature of the group delay characteristic of the original filter, non-corrected, it's difficult to get symmetrical 5% of both sides during the iteration process. Now at the end we are looking for solutions of group delay correction for bandpass filters. Here is a 14th order LSM filter which was obtained for the 7th order prototype. The order of the denominator, the number of transmission zeros of the bandpass filter before correction is 13 and the minimum stopband attenuation is 60. Four group delay characteristics are shown. The corrector is of order 2, 4, 6 and 8 and the group delay error is 1%. As one can see the interval is getting broader and broader during with the rise of the complexity of the corrector. This is the same diagram, but where the group delay is enlarged so that one can see better the approximation interval. And in this final slide we see the same problem, but the group delay error is 5%, and as we can see we cannot go above the 6th order since the whole passband is covered. This ends the 7th part of the series of lectures. Thank you for your attention.